Hey, good morning or good afternoon. This is Benjamin. I'm glad to be back. I think we were kind of on a summer break for a couple of weeks with virtual IoT, but now we have some really good sessions lined up for the next few weeks, and starting today with a session about RISC-V. So I don't know how many of you guys and new people watching us know about RISC-V. If you don't know anything about RISC-V, today is your chance to learn more. But if you do, if you are already a bit familiar, you will actually be glad to hear about some actual boards being made available to use RISC-V architectures, and especially in the context of IoT. So we are joined today by David and Mavi from SiFive, and SiFive is one of those companies who are actually building some really cool hardware. So I will let David and Mavi maybe introduce in a bit more details and the mic. Any questions, make sure to ask on the YouTube chat. I think that's the best option. Or you can also tweet using the virtual IoT hashtag. And yeah, that's basically it for the general announcements. Dave, Mavi, the floor is all yours.
All right, great. Thanks for the introduction. Hi, my name is David. I'm a product manager at SiFive. I cover the Freedom Everywhere and Freedom Unleashed platform, and we're here to talk to you and tell you about RISC-V and what we're doing in this space. So what is RISC-V? You probably kind of heard about this open source thing that's been going out there. Maybe you heard it's the open source CPU or something. Really what RISC-V is, it's a free and open instruction set architecture. The instruction set is really something where the software is how the software talks to the hardware, right? It's the little bits that tell the hardware or tells the CPU what to do. By making it free and open, it means that anyone can really build their own CPU implementation around it and leverage the fact that you already have a huge community of people building software and contributing to the software ecosystem. And you can leverage all the compilers that are being written for this and reuse a lot of it. In doing so, we have now multiple open source solutions with RISC-V, as well as we have proprietary CPU implementations using RISC-V. RISC-V was really designed to be scalable and customizable. How this works is there's really a really small subset, which is called the base instructions. This is like your add, your subtract, your branch instructions, and that's what everyone has to implement. And then on top of that, if you want to add things like hardware multiplies or you want to add floating point, there are extensions you add on top of that to enhance your CPU core even further. And so what that allows you to do is with that same instruction set, you can go from something as small and simple as a microcontroller all the way up to supercomputers. You can have something that's 32-bit, you can have something that's 64-bit, or it can scale all the way up to 128-bit computing. And next, with RISC-V, there's a growing software ecosystem. Because it's open, because we have a lot of people who have interest in building CPUs around it, a lot of people are contributing to this space. And so there are many open source tools that are available. There's also a lot of commercially available tools, tools that you're already used to and familiar with, as well as operating systems from around the world are being developed and ported to RISC-V. So we really believe that RISC-V is here to enable innovation and allow allow the instruction set to be free. The RISC-V Foundation was founded to basically maintain the specifications. So this is where all the members come together. We agree and ratify on different specs. For example, the base spec and the floating point specs, these are all frozen. And right now we are trying to ratify the vector extensions. We have security extensions. All that's happening at the RISC-V Foundation. And now we actually have a growing number of people joining the foundation. We have over 100 members now, both from academia, from industry, from all walks of life. They're all joining the RISC-V Foundation and contributing to this platform. So why is RISC-V really being embraced? For one, it's a very simple instruction set. And it's also free and it's open, which means overall the IP costs are going to come down. It's really architected for security with a very simple ISA. The problem with more complicated ISAs is, along with, as you know, with complexity, it's harder to verify and validate things. It's good to have something that's simple and easier to validate. The software ecosystem is maintained by more than one person. And so because it's maintained by everyone in the world, it's not restricted to just one company, and you're not locked in. And so really RISC-V allows you to have a lot of freedom. You can use your own solutions. You can use open source solutions. You can use commercial solutions. They're all available with different amounts of support and different amounts of capabilities, and it all depends on your requirements. But also, more importantly, allows you to differentiate. So you can add things like special instructions that speed up some calculations for your application. You can do a lot of specialization, some special optimizations in terms of CPU architecture for your particular application. It's really up to you, right? There's no one-size-fits-all computing nowadays, and RISC-V is really there to enable you to do more with it. Now, RISC-V, I think some people think it's something relatively new, and it is a new in terms of instruction set, but really it started back in 2010 at Berkeley. The first project for RISC-V was kicked off in May of 2010, and there's been multiple tape outs of RISC-V processors before finally coming up with a foundation in August of 2016 to really start to codify and ratify specifications for everyone. Sci-Fi itself, we were founded as a company by the inventors of RISC-V, really to promote and commercialize this technology everywhere. And so, we have base platforms like our first microcontroller platform called the Freedom Everywhere platform, as well as our Linux-capable platform, which is the Freedom Unleashed platform. We enable the community to build software on it, but providing the hardware for it. In addition, we have CPU cores that are available, as well as later we'll talk about also building your own SoCs with Sci-Fi. And going forward, we have a lot more people joining the foundation. Now, like as I said, we have over 100 members in RISC-V. There are new specs that are being developed, and really, it's an exciting time to be with RISC-V and see it grow. So with that, I'll introduce Maeve, who is one of our software gurus, and he will talk a little bit more about RISC-V instructions.
All right, hello. Hopefully everyone can hear me. I think we're gonna dive into some of the more technical details here. What I wanted to do with this slide is talk about the complexity of modern instruction set architectures. This example, this is the load multiple increment address instruction from the ARM instruction set architecture, and it's better known as a POP to us old CISC programmers. But I think that the way that ARM describes it here, it really gets to how complicated even a simple operation such as a POP can be. So as you can see, this one instruction, it loads multiple registers from the stack pointer. It increments the stack pointer. It will only do it if the equal condition code is set, and on top of everything else, it returns from the function call by moving something from the stack into the PC register. So hopefully you'll get an idea for how complicated even something as simple as a stack pop can be. So with the RISC-V instruction set, the designers of the architecture wanted to try to reduce a fair amount of that complexity. And I think we can move to the next slide. I think David's in control of that. Yeah, cool. So, right, so the motivation was that we're going to create a new clean slate design that's simple. And because it's simple, it can be implemented in a very small number of gates. And if you actually look at the implementations that are being built, not only by Sci5, but by other people as well, the CPU, the number of gates, which corresponds to the area on the die and the amount of power that's being consumed, is noticeably smaller. And I think, as David alluded to earlier, one of the ways that we did that was to eliminate what you might call extraneous instructions from the core instruction set architecture. We have this core. So if you see RISC-V, a RISC-V architecture description, it's going to be RV32 for the 32-bit, RV64 for the 64 bits, and you'll get a series of letters after it. The I after the RISC-V numbers stands for integer, but then there's a number of different standard extensions: hardware multiply, atomic operations, etc. Also, there's space in the instruction set architecture for you to create your own custom instructions. So you don't need to go to a central body to create a core with custom instructions. However, if you want other people to use them, or you want people to build software to use them, the RISCV Foundation is the right place to go to lobby for your maybe your private instructions to be made public and to be made a standard extension. So we think that what this is going to do is this means that our core functionality, the integer, branch, logical operations, hardware multiply, floating point, all that stuff is stable. It is currently in a stable frozen specification. But there are several extensions, some dealing with vector multiplication, bit manipulation, that are things that the designers didn't think everybody would want. A lot of people are going to implement them, but maybe not everybody. Maybe if you have like a very small application that just needs to test a sensor and send a bit over a serial port, well, maybe you don't need a vector multiply. Maybe you don't need all the bit manipulation instructions. So we have the ability to create a standard base, and that's stable now. The extensions are in the works, and I encourage everyone to participate in that process. You can go to RISCV.org, find out more information about that. Okay, let's advance the slide.
So Maeve, actually, if you don't mind, there's already a question actually from Alex on the topic of simplicity and footprint. And I will just read the question out loud. It seems like ARM tried to reduce the number of instructions in the 64-bit ISA. How about that? Is there a comparison to that ISA in terms of complexity?
Yeah, we try to avoid those kind of comparisons, and I try to avoid it primarily because I'm not necessarily an expert in ARM v8. I have much more personal experience with the old 32-bit ARM, but I will say that the designers of the RISC-V instruction set architecture, they were certainly looking at the way that ARM had developed, how ARM had evolved. Right, you started with a relatively small instruction set, that was 32-bit, and over time, people added more standard instructions, or I say people, ARM, in response to their customers' demand. And then 64 bits became a thing. We have the advantage that we did not have to. We had, with the benefit of hindsight, we saw what happened with x86 and with ARM, and we designed something to be extensible in a way that would cause maybe less disruption. But in terms of exact ISA complexity, I don't know how to quantify that, but I do believe, from looking at the 32-bit instruction set with RISC-V and the 32-bit instruction set with ARM, which is what I'm personally more experienced with, our instruction set is a little bit less complicated and less complex, and the extensions, if you don't implement the extensions, it's a lot less complex. Although, like I said, there are a number of standard extensions that many people might be implementing. I'm sorry I can't give you a number like we're 1.7 times more complex.
Yeah, no, that makes sense. So, thank you.
Yeah. But yeah.
But
talking about thanks for the question. I mean, talking about the complexity and extensibility, this slide is actually showing what our standard opcode formats look like. So this is for the really geeky people, right? So we have 4 basic instruction types. If you read the spec, you can dive down into this and figure out exactly what percentage of the 2 to the 32 bits, 2 to the 32 number of possible instructions are actually used. That's actually a good question. I should probably do that. That will allow me to give an actual answer, like this percentage of the 32-bit space is actually used. One thing I should point out: RISC-V is not a single instruction set architecture. It's actually 4 sub instruction set architectures. There's the one that or the 2 that I think you'll hear most about now are the RV32i and the RV64i. That's our basic 32-bit and basic 64-bit instruction sets. There is an RV128i there's space in the opcode space for 128 bits whenever the community thinks that we need to really spend a lot of time on it. So far, 64 bits has been sufficient for everyone. So but there's the RV32e, which is even smaller. It's the same instruction set, but it assumes that you only have 15 registers instead of 31 registers. And so that's orthogonal to the standard extensions. So if you had an RV 32E, it would still only implement the basic I instruction set. And we're listing the standard extensions that we have. There's a hardware multiply divide. Again, not everybody implements that. Floating point, we have single and double precision. The compressed instructions are very important. It's the equivalent to thumb. We can have a 16-bit instruction. We are not modal in that you don't have to be in 32-bit mode or 16-bit mode. The way that our instruction decode works is we look at the lower 2 bits of the instruction, and that will actually tell us whether it's a 16 or 32 or 64-bit instruction. The instruction, how the instruction will be decoded. There's also atomic operations, which are your load, increment, store, all as one atomic operation, which is extremely useful if you have a multi-core design. And and I see that someone is asking, is there an RV64E? I don't believe so. You are free to go off and try to create one. I mean, the instruction set architecture is open. I think that, if you try to call it RISC-V, you might, the RISC-V Foundation may have a couple issues with that. They would like you to come and participate in the process and join the foundation before trying to do that.
I think it's better if you submit it to the committee and see if see if the standards body will approve of it.
Yeah,
I mean, if there's a need for it, let's see.
Yeah. Yeah, but I mean, I will say that the primary motivation behind the RB32E was to target much smaller applications. Like I said, we reduced the number of working registers from 31 to 15, and part of the reason we do that is so that they can all fit in the compressed instruction space, or more registers can fit inside the compressed instruction space. And if you had a 64-bit, well, then you'd have larger instructions because you'd be trying to load 64-bit values into registers. I mean, it's not, I don't think it's completely outlandish, but the initial motivation for the RB32E was to go smaller and not necessarily wider. Okay, and hopefully that answered the question. So, okay, let's go ahead and hit the next slide. Okay, and one of the cool things about RISC-V is the ecosystem. I have been extremely impressed by how quickly the ecosystem has developed. I mean, it's really quite astonishing. Sci-Fi, well, I shouldn't say Sci-Fi. The founders or the inventors of the RISC-V instruction set architecture, started working on GCC tools and the bin utils when Sci-Fi was formed. Sci-Fi now funds some of that development, along with I think Andy's, and I probably shouldn't mention too many other names because I know I'm forgetting people. The community as a whole funds the development of GCC, but there's also this really cool commercial. Oh, I got ahead of myself. Sci-Fi Freedom Studio is a IDE based on Eclipse, which is an open source project, and it bundles Eclipse, GCC, bin utils, OpenOCD, so you can have a nice environment to do development. But yeah, then getting back to the commercial side of things, there's actually a very quickly growing commercial ecosystem. Sager, Lauterbach, Ultrasoc, IAR, all these guys are participating. I am quite familiar with the free RTOS on RISC-V, but the guy who sits next to me is working on Zephyr. Although there's also Thread Logic and Riot. On the 64-bit side, on the Linux capable side, we have a build root Linux. There's a open embedded environment that's available. Fedora, the Fedora maintainers are working on a version. I spend a fair amount of my day working on Debian Linux for RISC-V, and it is pretty much all there. I mean, when I give demos of Debian for RISC-V, people are just kind of amazed by, well, it just looks like Debian. It's like, yeah, that's the point. It works. There's nothing special about it. And let's go to
how about LLVM support? Edward is asking.
I'm sorry. What was it? Which support? Oh, LLVM. Okay. LLVM support. I think it got kicked off a while ago, and it kind of languished for a while. We are also funding a guy to work on LLVM, but I will tell you that LLVM development for RISC-V is kind of far behind GCC. But it's getting work done.
Okay, thank you.
Okay, and then oh yeah, let's go ahead and move forward a slide. And so this is our Arduino compatible board. This is probably, for this group, is probably the most interesting board that we make. It is a 32-bit RISC-V system. You can use a command line IDE to develop for it, or you can use Freedom Studio. It's basically an Arduino system. We also, oh, you know what? We also have an Arduino IDE. We have Arduino IDE support. I keep forgetting about that because I don't use Arduino on a daily basis. But if you are an Arduino guy, it works. Yeah, let's go on to the next slide. And this is our dev board for our 64-bit part for the FU540, and it is a much beefier board. Oh, I guess we're putting 8 gigabytes. the board I have that I worked with only had 6 gigabytes, but now I guess we're doing 8 gig. But yeah, it has everything you need to boot Linux. So what most people will do is they'll put a SD card, a micro SD card with a Linux kernel and a file system in the SD card reader, and just turn it on. And like I said, a lot of people are just kind of amazed. It looks like Linux. Well, because it is Linux, and it just works. And I think with that, I'm going to yield the rest of my time to David, because I think we're starting to run out of time.
Yeah, just remember you can purchase both these boards from Crowd Supply. Links down there. Okay, so why is RISC-V important, and why now? I think we've all heard and we all now know that Moore's law is really coming to an end. We're not getting better performance as we shrink the die, or as we shrink the processes. We're getting lower power, but for each generation, it's costing us more and more to get there. And so we don't really get that instant benefit of going through process shrink. So what this means is now we got to go back and start focusing on architecture and really starting to target and rethink how we build up these systems and target them for the application. We can't depend on the process to kind of just naturally give us this magical boost in low power and better performance. And so, going forward, we don't believe that general purpose solutions is going to be sufficient to meet all the application needs. We're going to probably be sticking around with a lot of these process nodes for a very long time, going to 7 nanometer and beyond. I think there's just fewer and fewer and fewer companies who are just going to be able to go that route. Mostly because of cost reasons, and there's not every application needs to go to such nodes. And so what's great is that now we should really go back and start looking at what does my application need? How do I really take advantage of the silicon that I do have and not waste it by putting a lot of dark silicon on there or adding a bunch of stuff that other people need, but I don't really need it for my application. So we really need to start architecting the system, the overall system for low power. So whether that is, I need to have look at the CPU architecture to say, I don't need a superscalar for this solution. I need something that's very simple in order processor. Maybe I don't need 64-bit. 32-bit is sufficient for my application. Maybe it's better to have a lot of little cores as opposed to one big superscalar core. That's all going to depend on your application. And RISC-V is there to allow you to kind of tweak and tailor it to meet your needs. More importantly, I mean, we've all bought general purpose solutions off the shelf, and we're like, well, wouldn't it be great if we had one more of a particular peripheral, or wouldn't it be great if it came in a different package, because that would fit better in my product. Or it wouldn't be great if it could actually, go to really a low power sleep mode and I could turn off this rail and maybe not turn on that rail. What that means is now, we have the ability to go and pick and choose, right? If we can start building our own custom processors and custom ASICs around it, we can really start to pick what we need and not burden ourselves with just buying these general purpose things where it's really an amalgamation of a variety of people's different needs. And like most general purpose things, they're great for mass market, they're great for cost, but overall they don't always match or meet the solutions or meet the problems that we need to try to solve. And of course, leveraging open source, leveraging the fact that there's a lot of IP that's already available. Really, we should be focusing on what really matters to your application, right? There's no need to rewrite, for example, an I2C controller. I mean, it's a very simple interface. So why do we do it every time we go to different processes, right? Why do we do it when we go through different processes that we buy? So really, we should leverage and reuse IP where possible. We should leverage open source where possible. And then you focus on things that you're good at. Like maybe you have a special accelerator or you have a software algorithm. You should be focusing on that as opposed to building up things like operating systems. So really, we believe that now is the time to start building custom SoCs, especially for the IoT market. So with Sci5, what we have is, we have that ability, and we're trying to enable people to be able to do that. And so we have, two real main products. We have the Sci5 Core Factory and a Sci5 Chip Factory. With Sci5 cores, you can build custom soft CPU IPs, which you can load into FPGAs. You can put into ASICs. But more importantly, we have something called Chip Factory. And with Chip Factory, what that allows you to do is take some of our CPUs, take IPs together, and Sci5 will build you a full prototype as well as production ASIC for your application. So we really have right now we have two classes. We have the Freedom Everywhere platform, which is targeted for 32-bit microcontrollers. Currently, it's on the TSMC 180 nanometer process. There's digital and analog peripherals that are available for it. And it's really targeted for smart IoT devices, wearables, embedded. And then, of course, we have a Freedom Unleashed platform. This is where we have the higher performing 64-bit multi-core solutions, but they could also be embedded controllers as well. The main differentiator here is that now it's on TSMC's 28 nanometer process. So it is a smaller process, so you can fit more things onto it. It's a little bit leakier than the 180 nanometer, but its dynamic performance is better. We have cache coherent support. We can add on a lot of special accelerators. There's higher speed modern peripherals that are available on 28 nanometers, so we can take advantage of things like PCIe Gen 3, Gigabit Ethernet, DDR, and we can target things like data centers, storage, SSD controllers, networking, baseband, and even IoT gateways. We have a program called Design Share where third-party IP providers are joining to provide their IP on our platform that you can pick and choose from for you to build your own ASICs as well. And so when you combine the third-party IP, you combine Sci5 CPU cores, you can combine open source IP, as well as you may have your own custom IP that you want to onboard and put into silicon. You can come to Sci5's Chip Factory, and what we will do is we will put all those pieces together. We will get the prototypes as well as production chips fabbed at the TSMC. It will come packaged up, and what you get is packaged chips. So you can now really start to build your own customizable SoCs for your IoT applications. And Sci5 really manages all the complexities of having a large back-end team that will do the layout for the chip. We take care of actually taping out that chip, going through all the way through packaging, so that you don't have to worry about the logistics of that, which typically requires a large team behind it. Okay, and so for more information, you can visit us at www.sci5.com.
All right, thank you very much. So I think we actually had a lot of questions during the presentation, so I'm not sure we left any of those questions unanswered at this point. There's certainly a few more minutes for people to ask, and well, the webinar is recorded, right? So you can always post in the comments, and we will make sure to let David and Maeve know should you post a question after we go off the air. So yeah, that probably leaves me with well, first some time to thank you guys for this presentation. I think this was great to see the progress on RISC-V over the past few months and few years, but it will also be great to see what's coming next. So, and especially for IoT. I think we're back next week for another virtual IoT meetup, talking about security. And when Roxanne and I did a look at all the virtual IoT, we actually were pretty sad to see that we hardly ever did ever had any session around security. So I'm glad that we're joined with someone from GrabHub actually next week to talk about security. You will also see on meetup.com that we are organizing an Eclipse IoT Day in Singapore on September the 18th. So this might be a long way for some of you, but this might be local for some others. So if you're in the area, please check this out and just let me know if you plan on attending. It would be great to catch up. And do I see more questions at this point? I do not. So again, David and Maeve, thanks so much. I think having been on your website on a number of occasions, I think people will definitely find lots of information there. And yeah, like I said, looking forward to see what's next for the RISCV ecosystem and for Sci5.
Thank you.
Thank you so much.
Thank you. Bye.